Hello, and welcome to this presentation related to the graphical solution of linear and quadratic simultaneous equations. Within this presentation we'll be given two equations, one in the form of a quadratic equation of the form y equals ax squared plus bx plus c, and one in the form of a linear equation y equals mx plus c. For the graphical solution, we evaluate coordinates related to each of these equations and then plot the respective equations on a graph. For the graph shown, this would be the quadratic equation plotted, this would be the linear equation plotted, and where the lines intersect are the solutions. So this is the first solution, and we read off the appropriate x value and the appropriate y value. And the second solution occurs here, and again we read off the appropriate x value and we read off the appropriate y value to form our solutions in terms of x and y. Although this presentation predominantly relates to graphical solution of linear and quadratic simultaneous equations, within certain questions I will also outline the analytical solutions purely for reference. This presentation does assume some previous knowledge. So an overview of the techniques required for the graphical solutions, you need to be able to plot linear equations of the form y equals mx plus c. You need to be able to plot quadratic equations of the form y is equal to ax squared plus bx plus c. And also it's beneficial to be able to sketch the characteristics of linear and quadratic lines. There are separate presentations on plotting linear lines from equations and also plotting quadratic lines from equations. This presentation will also outline analytical solutions to certain problems, and if you want to be able to follow those, you need to be able to transpose equations and also to solve quadratic equations using either the factorization or the formula method. However, the main focus of the presentation is on graphical solutions. Graphical solution of linear and quadratic equations. To solve simultaneous equations with one linear and one quadratic equation, a graph is to be plotted and the solutions are found where the equations intersect. Example 1s. We're asked to solve simultaneously the following equations. The first one is a quadratic equation, y is equal to x squared plus 3x minus 4. We've called that equation 1. And the second equation is a linear equation, y is equal to 2x plus 4, equation 2. So the first thing we need to do in our solution is to find the range of x values over which to plot the two equations. And to do that, we're going to consider a sketch of equations 1 and 2 above. Let's consider equation 1 above first of all. That's a quadratic and that has the form of y is equal to ax squared plus bx plus c. Reading the values of a, b and c from equation 1, the a would be 1. There's a 1 in front of the x squared we don't write, but it's there. The b in this case would be positive 3. Don't forget the sign in front of the numbers with it. And the c would be negative 4. Now from our previous presentation related to plotting quadratic equations, we know that the constant a, if it's positive, which is in this particular case it's positive 1, it will plot a curve that has a parabolic shape in the form of a bucket. If the a value was negative, it would be still a parabolic shape, but in the form of a hat. We also note from previous work that the parabola's vertex, that's the bottom of the curve if the a is positive, and the top of the curve if the a is negative, has an x location given by the equation negative b divided by 2a. In equation 1, we know that the b value was 3 and the a value was 1. So putting the values of 3 and 1 into the equation, we have the negative 3 for the negative b term on the top line. That's divided by 2 times the a, that's 2 times the 1 on the bottom line. So that gives a x location for the vertex at negative 1.5. We'll show how that's used in a moment on the next slide. That means that the vertex is located to the left-hand side of the vertical axis, the y-axis. And constant c, again from a previous presentation, relates to the intercept of the parabolic curve with the y-axis. And so the intercept here is negative 4 on the y-axis. Example 1s continued. Let's now consider equation 2, which is the equation of the straight line, and that has the form y equals mx plus c. Again, from previous work, we know that the m in the linear equation relates to the gradient or the slope, and the constant c relates to the intercept of the line with the y-axis. Equation 2 on the previous slide has a gradient of 2, so the m value is 2, so that means it's 2 in 1. That's a rise of 2 in a distance of 1, and the gradient is positive, so that means it's like walking uphill on the graph as we move left to right. The intercept of the linear line with the y-axis, the c constant, is positive 4 in this case. So the line crosses the y-axis at x is equal to 0, y is equal to positive 4. Here's a sketch of the two equations. So this is our quadratic curve, which produces a parabolic curve, form of a bucket here with the vertex at the bottom of the bucket. And here's our linear line with the gradient of positive 2. The intercept with the y-axis for the quadratic is at negative 4. The intercept with the y-axis of the linear line is positive 4. We calculated on the previous slide that the vertex occurs at x is equal to negative 1.5. Here's the location of the vertex. So the benefit of being aware of the characteristics of a quadratic and a linear equation is that we can sketch the form of the equations and so find the range of x values to use. So in this particular case from the sketch, we would say we've got a range of x from say negative 4 through to possibly positive 3, positive 4. And that's the range we're going to use. We're going to use x equal to negative 4 and x is equal to positive 3. On the next slide, we'll actually now plot these equations. Example 1s continues. So we're going to evaluate now the coordinates. We know that the range of x we're going to use is between negative 4 and positive 3. I'm using increments of 1 here to try and give me a nice defined shape for the curve. We need to now work out the y values for the quadratic equation and of course the y values for the linear equation. We can see that the table is partially populated with some of the y values being calculated. I would now encourage you to stop the presentation and fully populate the table, working out the y values for equation 1 and then working out the y values for equation 2. If you then want to progress the solution by plotting the lines on the same graph, you will find the solutions are given here. I have included the full work solution on the following slides. So example 1s, we're solving the two equations simultaneously, equations 1 and 2 repeated for convenience, and here's the fully populated table evaluating all the y values for equations 1 and equations 2, given our range of x values of negative 4 through to positive 3. On the next slide we will actually plot the coordinates. Example 1s continued. So here's the plot of the equations. So here's the quadratic equation plotted from the values stated on the previous table. And here's our linear line. Again, it's plotted from the values calculated on the previous table. The solutions are where the two lines intercept. So we have one solution here, which reading on the horizontal axis, the x-axis, that would read in the region of 2.4, looking at our scale. And reading on the vertical axis, that would read in the region of 8.7, again given the scales involved. And our second solution is over here. And again, reading the x-axis value, that would be in the region of negative 3.4. And the y value, again, estimating it would be in the region of negative 2.7. So our second solution here. So that's how we solve simultaneous equations relating to a quadratic and a linear equation and find the solutions located at the intercept points. On the next slide, I will show the analytical solution for reference. Example 1s continued. Here's the analytical solution to the example. Some of you may prefer to skip this part of the presentation and concentrate on the graphical solutions. So that's fine if you want to do that. Skip a few slides and you'll find some questions that are given to us to solve graphically. For those of you who want to see the analytical solution to example 1s, here's the first part of it. We're given the two equations, this equation 1, our quadratic from the previous slide, and our linear line equation from the previous slide, equation 2. And what we do now is equate the equations. So on the left hand side I have x squared plus 3x minus 4, the quadratic equation. On the right hand side I have 2x plus 4, the linear equation. To rearrange the equations by bringing all the x terms and the constants from the right hand side to the left hand side. So the x squared term remains the same, but I subtract 2x from both sides of the equation, so that leaves me with plus 1x or plus x on the left hand side, and I subtract 4 from both sides of the equation, so negative 4, and then we subtract 4 from it, it becomes negative 8, and that now equals to 0. What we have now is a generic form of quadratic, the ax squared plus bx plus c equals 0 format. So we can now solve the quadratic equation by using the formula. Again, previous presentations have reviewed the solution of the formula. I'm just stating it here. The negative b plus or minus the square root of the b squared minus 4ac all divided by 2a, standard quadratic formula. And reading from above, we can see that the a term is 1. There's a 1 there we don't write, but it's there, so a is equal to 1. See that the b term is also 1. There's a 1 here we don't write, so b is equal to 1 in this case. And the c term is negative 8 in this case. C is negative 8. All we do is put those values of a, b and c into the quadratic formula and evaluate. I'll let you work through the evaluation shown here in detailed breakdown. Don't forget in the quadratic equation we have this plus or minus, which means we have two solutions. So the first solution I've denoted x1. We'll use the plus sign here in the numerator, and that evaluates to 2.372. Example 1s continued, just repeated the first solution x1 value from the previous slide. Don't forget we evaluated that from the negative 1 plus the square root of 33 divided by 2 to give us a 2.372. What we're going to do now is work out the y value associated with the x1. So to find the value of y1, we're simply going to put the value of x1 into the original quadratic equation given to us and evaluate. That gives us a y1 of 8.74. If we want to, we could check that value by using equation 2, which is a linear equation. So putting the value of x1 into the linear equation given to us, we also find that the y1 is 8.74, so it checks out. So the first solution found from the analytical method is x1 2.37, y1 8.74 to 2 decimal places. So now I'm going to find the x value for the second solution. I'm going to call it x2. And now we have the negative 1 minus the square root of 33 all divided by 2. That evaluates to negative 3.372. Again, to find the y value, I will use equation 1. So the y2 in this case, putting the value of x2 into the original quadratic equation given to us and evaluating, we will find that the y2 is negative 2.74. And again, if we want to, we could check that with equation 2, the linear equation. So y2 evaluates 2, putting the value of x2 into the linear equation given is negative 2.74, so it checks out. So our second solution in this case is x is negative 3.37, y is 2.74 to 2 decimal places. So that's how the analytical method would be used to solve example 1s. It's just for reference. Here are some tutorial questions related to the solution of linear and quadratic equations. Got to solve simultaneously the following equations. So question 1s through to question 4s has given us equations to solve. Just be careful of the way the equations are expressed. In question 1s, this first equation is in the right format of y is equal to ax squared plus bx plus c, but the linear equation here needs to be transposed to make y the subject. Again, I would encourage you to sketch the two lines and estimate where the intercepts occur, and so the range of x values over which to plot. Coordinates to the two solutions are shown here. I would encourage you to stop the presentation and attempt questions 1s to 4s using the graphical solutions to solve for the answers. If you want to also apply the analytical method, then please feel free to do so. I will work through some of these solutions on the following slides. Note for reference, question 5s is a contextualized problem where we need to actually apply Pythagoras' theorem and also the formula for the perimeter of a rectangle. So we need to apply those techniques to generate the two equations in this case. One will be a linear line, but the other will be a non-linear line. It will not be of the form of quadratic, but it will be a non-linear line. And as with all the solutions we reviewed, you'll have to rearrange the equations to make y the subject on the left-hand side of the equations. So one equation will be in the form of y equals mx plus c, but the other equation will be in the form of y is equal to a non-linear function. But the rest of the solution then will be as we've outlined previously. Again, if you think you can attempt question 5s, I would encourage you to stop the presentation and try that question, but the full work solution will be shown later on in the presentation. The answer to question 5 again is shown in the brackets. Here's the graphical solution for question 1s. We're given a quadratic equation and a linear equation. Just note we have to rearrange the linear equation to get the y as the subject. So in this case, I would just simply add y to both sides of the equation, so the y is equal to x plus 2. The quadratic equation was in the correct format to use. Again, from estimating the range of x, I've used negative 2 to positive 4 in increments of 1. And I've calculated the y values from the equations. Plotting the graph, we find there are two solutions, one here and one here. And simply reading off the graph, the first solution occurs at x is equal to 4 and y is equal to 6. So that's my solution here. And my second solution is over here. X is equal to negative 1 and y is equal to positive 1. If you want to follow the analytical solution, it's very similar to that shown for the example 1s. We simply equate the two equations together. So this is the first equation, the quadratic, equated to the rearranged linear equation. Then rearrange the equations to form a quadratic equation, form ax squared plus bx plus c equals 0. Question 1s continued. But in this case, I'm solving the quadratic by factorization. Again, a method we looked at in a previous presentation. Using the factorization method, the first thing we determine are the factors, in this case x plus 1, x minus 4, and then we equate each of the factors to 0 to solve for the roots. So in this case, the roots are x is equal to negative 1 and x is equal to positive 4. And to find the value of y1, I simply put the value of x1 into equation 2 in this case. So that evaluates to a y1 of 1. And to find the y2, I'm using the linear equation again, put the value of x2 into the equation, evaluates to a y of 6. So we can now see we've got the same solutions as that from the graphical method. Negative 1, positive 1 for one solution, and positive 4, positive 6 for the second solution. Question 2s, here's the graphical solution. This time we're given the two equations in the correct format. The quadratic is in the correct format, and so is the linear equation. My range of x in this case from my sketch was -2 to +6, and I evaluate my y coordinates for both equations, and again plotting the lines on a graph. Again, we've got our two solutions, one shown here, x is equal to 3, y is equal to 11, reading my graph, and the second shown here, when x is equal to 0, y is equal to 5. I'll let you review that solution at your own pace. Question 3s, graphical solution, solving the simultaneous equations given. Again, the quadratic equation and the linear equation are already rearranged in appropriate format for us. The range of x values I've used here is between -1.5 and +2. Worked out my y values for the two equations and plotted the lines on the graph shown here. We can see the lines intercept here, so I've got a root at x is equal to 1 and y is equal to 3. And my second solution is down here, and that's x equal to -0.2 and y is equal to -3. I'll let you review that solution at your own pace. Question 3s, here's the analytical solution if you want to review it. Again, we're given our two equations, which are equated here, and then rearranged to form a quadratic, which we're going to solve in this case using the quadratic formula. I'll let you review that solution at your own pace, find out how we determine the value of x1, and the solution is continued on the next slide. Question 3s, analytical solution continued. Just repeated the x1 value from the previous slide for reference. Now we're going to work out the value of y using equation 2, which was the linear equation on the previous slide. So y1 is equal to 5 multiplied by the x1, which is 1 in this case, minus a 2, so that's equal to 3. So our first solution, when x is equal to 1, y is equal to 3. And to find the second solution for x2, notice a change of sign here in the numerator when we're evaluating x2 compared to x1. That relates back to our quadratic equation. So evaluating x2, that becomes to -0.2. Again, calculating y, I'm using equation 2 again here, linear equation. y2, using the value of x2 above, evaluates to -3. So our second solution in this case is x is equal to -0.2, y is equal to -3. And these are the exact solutions to the question. Question 5s is a more difficult question because now we've got a contextualized problem where we have to generate the equations from the information given. We're basically told that we have a rectangular plot of land that has a perimeter of 280 meters. So adding up all four sides, it totals to 280 meters. We're informed that the length of the diagonal is 100 meters. So on my diagram, here's my length of diagonal, 100 meters. So here, and I've labeled the sides x and y. So the question wants us to determine the plot's dimensions. So in other words, we've got to find the values of x and y. So if you like some hints on how to generate the equations, let's consider the first sentence of the question. A rectangular plot of land has a perimeter of 280 meters. In other words, we're adding up all four sides and we get the value of 280. So using the notation given, 2x added to 2y would equal to 280. There's our first equation in terms of x and y. Reading on, we know the length of the diagonal drawn corner to corner is 100 meters. So using Pythagoras' theorem here and notation in the diagram, we could write x squared added to y squared is equal to 100 squared. That's applying Pythagoras' theorem to our problem. In other words, square of the hypotenuse, 100 squared, is equal to the sum of the squares of the other two sides. What you need to do now is take the first equation and rearrange it in terms of y. That will form a linear line of the form y equals mx plus c. And then consider the second equation here, rearrange that to make y the subject, that will not be in the form of a quadratic equation, but it will be a non-linear line when plotted. So the basic process here is the same as in the previous questions. It's just that one equation is a linear line and the second equation is a non-linear line, but not of the form ax squared plus bx plus c. And again, you'll plot the two lines on a graph and look for where they intercept for the solutions. If you think you can solve the problem from here, I'd encourage you to stop the presentation and attempt this question, but the full work solution is shown on the following slides. Question 5s, here's the full work solution. So here's the first equation related to the perimeter that we generated on the previous slide, and we need to rearrange that in terms of y, which is shown here, equation 1. And we generated this equation from Pythagoras' theorem on the previous slide, and again that has to be rearranged for y, and that's shown here as equation 2. Note that equation 1 is a linear equation of the form y is equal to c plus mx. And note the second equation is not of the form of a quadratic equation, it's not in the form of ax squared plus bx plus c, but nevertheless it will plot a non-linear line on the graph. The solution process is exactly the same for solving simultaneously a linear and a quadratic equation. Question 5s continued. My range of x values I used here was between 0 and 100 meters in increments of 10, and I worked out my y values for the two equations. Plotting the graph, you'll see there are two solutions. One shown here when x is equal to 60, y is equal to 80. Also one shown here when x is equal to 80, y is equal to 60. I'll let you review that solution in your own time. For reference, here's a bibliography used to help with the development of the presentation. And I hope this has been of help to you. Thank you for viewing.